All right. 4.3, the fundamental theorem of calculus. Fundamental theorem of calculus. All right. So from the fundamental theorem of calculus, we have multiple parts. We'll have part 1 and part 2. We'll start off with part 1. And with that part 1, we have that there's going to be an equation defined using the following. So let me change color here. So fundamental theorem of calculus, part 1. And FTC just represents fundamental theorem of calculus. Okay. Well, the functions that are being used in that fundamental theorem of calculus has the equation of the form g of x is equal to the integral from a to x of f of t dt. So that g of x is the function that we'll be focused on, and it's defined by using the integral here. Now, f is continuous on your closed and bounded interval from a to b, and notice how there's an x value. Your x varies between a to b as well. So to kind of envision what this function looks like, just imagine for the moment that you have your y and t, you have a random function. We'll call this y equals f of t. And let's call this value right here a, and let's even right here b. So we have f being continuous from a to b. You can see that it's continuous from here to here, and x is somewhere in between. So let's say that x is like right there. It's between a and b. And so what happens here is that g of x, well, that's the integral from a to x. And remember that the integral, we can think in short right now that it's the area under the curve. So when I think about what the right-hand side of it is, the integral from a to x, that's the area under the curve drawn and shaded below. And what does that represent? Well, that's my g of x. So the area here is essentially equal to my g of x for that particular x. Okay. Now, to understand what this is, we will do a few examples. And but before I move on, just remember for the moment that x can be fixed, and then we get the area under this blue shaded region, and so that's just a number. But this x doesn't have to be exactly here. It could have been closer to a, closer to b. It could have been different. So that's why g of x is a function. It could be different values because your integral on the area under the curve is different values. So now thinking about an example, if I gave you a diagram of f, so given f, and we know that g of x is equal to the interval from 0 to x of f of t dt. That's how we'll define it for now, where a is just 0, right, from the above. I want you to find g of 0, g of 1, g of 2, g of 3, g of 4, g of 5, etc. Okay, here's the function that we'll work with. Here's your function, and at 0, 0 is a key point. If we can kind of scale this properly. At 1, we get 2. And then at 2, we get 2. And then from 2 to 3, kind of curve. Oh, hit 0 there. I think I need more space. So let me redraw this real quick. Sorry. I need a little bit more space. There we go. So again, 1, 2 is important. 2, 2, 3, 0, 4, and 5. So the 4 goes all the way down to -2. So from 0 to 1, you have this straight line segment, and then we have this horizontal line segment, and then from 2 to 3, for your t values here, it's kind of curved, so it's not completely straight. And then using that same kind of curve, I'm going to curve from 3 to 4, and then the same kind of curve back up to 5. Okay, so if you're given this, I want you to find what g of 0 is. Well, g of 0 is just the integral from 0 to 0 of f of t dt, where the function that I drew was y equals f of t. And if that's the case, well, what's the area under the curve under a point essentially that's already hitting the x or t axis? It's just 0. Well, what is g of 1? G of 1 would be the integral from 0, I'll scroll up so we know what g of x is defined as, is from 0, and then your x is 1 in this case, of f of t dt. And when you do that, if I look at the image, I'm going from 0 to 1, and I want the shaded region right here. And you'll notice that this is just simply a triangle. So because we're thinking of area under the curve, especially since I don't have the specific function for f right now. So I could just think of it as 1/2, the base of that triangle is 1, times the height, which is 2, so I get 1. So g of 1 is just 1. Now g of 2 will be the integral from 0 to 2 of f of t dt. Well, that would be from 0 to 2, so you can see that right here is the red part that I want, the shaded region of the red part. Well, remember, we have properties of integrals that I can separate it from 0. Instead of going from 0 all the way to 2, I could do from 0 to 1, and then I can add the integral from 1 to 2. Okay, so that way I get the rest of it. And so if I look at that first part, we already know what this first part is because that's just g of 1, which we figured out earlier was 1. Now over here, notice the shape from 1 to 2. That's just a rectangle. So that is just the base, which is 1, and the height of that rectangle is 2. So it's just essentially 1 plus 1 times 2, which is 3. Okay? So we're just seeing it as area of a triangle and area of a rectangle. And I can continue this process. So if I go to g of 3, that's the same thing from the integral from 0 to 3 of f of t dt. Now notice, since I already know all the way from 0 to 2, I could think of it as the integral from 0 to 2 of f of t dt plus the integral from 2 to 3, the part that I haven't figured out. And what is the integral from 0 to 2 of f of t? That's just g of 2, and g of 2 is just 3 plus, I'll just write that first. G of 2 plus the integral from 2 to 3 of f of t dt. And so I know that the first part, right here, this region in green is 3. However, this region that I'm going to shade in green, but in the other direction for the moment, I don't know that. However, I can at least estimate, because if I drew this part, this triangle that I'm shading in very clearly, that's the same thing as from 0 to 1, which we knew was 1. The area of this triangle is 1. So you can see it's a little bit more than 1, but definitely not more than this rectangle that I'm outlining, which has an area of 2. So between 1 and 2. So an estimate would be like 1.3. Okay? So then we get that this statement is now approximately 3 plus 1.3 is approximate because of the 1.3 aspect, which is coming from this piece, which equals 4.3 then. So g of 3 is approximately 4.3. Now, if I continue further, let's see what colors I have. Light blue. For the values of t being greater than 3, you notice how the curve is below the x-axis. So then, for t being greater than 3, we know that your function f of t happens to be negative. And so which is going to cause us to have to subtract the areas from the above minus the one from below, and the areas of the rectangles below, sorry, not areas of the rectangle, the area of what we get below because of the height relatively, if we're thinking of terms of rectangles, will be negative. So when I think of g of 4, this would be the same thing as the integral from 0 all the way to 4, but I'm breaking it up into 0 to 3 first. So that's the integral from 0 to 3, which is just g of 3, plus the integral from 3 to 4 of f of t dt. Now if I have that, going back up, we already know how much it is all the way from 0 to 3, but now I want this extra region down here. And notice it has the same height of 2, but negative. And the base is 1, so 1/2 base times height gives you that area of 1, but it's a little bit more than that. And I try to draw my picture the same exact way from 2 to 3, but just below the x-axis. So it's approximately 1.3 as well. So g of 3 was approximately 4.3, but now I'm adding my negative 1.3 from my approximation of this, and I get 3. Doing the same concept, g of 5, that will be equal to g of 4, the integral from 0 to 4, which we already know, plus the integral from 4 to 5, our last little piece. And because of the way that I structured it and drew the picture, this is approximately 3 plus another negative 1.3. If you go back up, this portion, this other half, is also about 1.3, but negative. All right, now let's do an example of a concrete example first to kind of think about what I'm going to lead to for the fundamental theorem of calculus. So first off, hopefully you can prove that the integral from a to b of x dx is equal to b squared minus a squared over 2. Let's say that this is already done. Okay? And so now let's think about my function. If your function f of t happens to be t, and your a happens to be 0, well, what does that mean my g of x is? Well, generally speaking, it was just from the integral from a to x, but a is 0 now, and I'm going to x still, of my function, which is t, dt. And if I were to do this, right, if I look at my proven information above, I get that my a is 0, my b is where my x is, because it's the upper limit, and x is my t, precisely, so I can use the formula above. And so I get x squared minus 0 squared over 2, which is just x squared divided by 2. So hopefully you notice in this particular example right now, how would you compare f and g? Well, g of x is x squared divided by 2. So if I took the derivative of g, or try to find the derivative of g with respect to x, isn't that just x? So what did we just get for this example? G prime, or the derivative of g, is just f, because that's f of t equals t, but I could have said f of x equals x kind of situation, right? But this also, if you look at the connection, is that if G is the integral of f, that's what we started off with. G is defined as the integral from 0 to x of f of t of dt. The result that we got was x squared divided by 2, which is also the antiderivative of f, right? G is also the antiderivative of f, right? If I gave you x, if f of x is x, the antiderivative is x squared divided by 2. Now, if you want to connect this back to what we did earlier, which I forgot to draw the graph, I apologize. Let me draw the graph of G. If I draw the graph of G here from my previous example, I get what values? So G of 0 was 0, G of 1 was 1. So G of 0 is 0, G of 1 was 1, G of 2 was 3. Here's 3, here's 2. And G of 3 was 4.3. And then G of 4 was 3. And G of 5 was 1.7 approximately. And again, I could have taken points besides 1, 2, 3, 4, 5. I could have done like 0.1, 0.2. And so this would have been connected, and you would have gotten a continuous function. And this is your G, right? And so what I was trying to say here, if I wanted to connect this, if I take the derivative of G, well, looking at this picture, taking the derivative of G, let's look at the derivative of G at 3. That's the, you think of tangent lines when you think of derivatives and its slope. And what is the slope here? This would be 0. If you go back to my original diagram above, at 3, f of 3 was 0, which is precisely what we get in terms of connection. Alright? So we can also see that when we look at G and its derivative, is the slopes of the tangent lines, which gives you the values of f. So last little note for this. Also, if the derivative of G is the slopes of the tangent lines, then we essentially have the values of f as I kind of go through it, besides just at that particular point. Now that we have an understanding of what g of x is, because we're defining it as the integral from 0 to x of f of t dt, let's get a brief idea if that's always true. Is g prime equal to f, the original function? So let's get some truth behind it. So the idea of the truth. Is g prime equal to f? Like, is it always the case? Well, let's take any continuous function. Any continuous function f with, for simplicity, that the function values is greater than or equal to 0. This tells us that g of x, which is the integral from a to x of f of t dt, is going to be the area under the curve. But if f of x is greater than 0, then that means the area under the curve should also essentially be positive, right? So let me write this part right here. Remember that this is just area on the curve. Of f from a to x. And so what does the derivative look like? Well, what does g prime of x by definition? of derivative. Okay, let's draw a picture. If I gave a random situation, here's your function f, and let's say that this is a, and let's say over here might be b, doesn't matter, and this can go on, but let's just focus within this realm. Well, if you remember the definition of derivative, I'll put a recall here if you want. It's the limit as h approaches 0 of g of x plus h minus g of x divided by h. That's the derivative of g. So for an h value being greater than 0, what is g of x plus h minus g of x? That's the numerator of the definition of derivative. Well, what we just learned just now was that if x is between a and b, so let's call this x real quick, g of x will be from a to x, which is this region in green. But then, if h is a little bit greater than 0, but I'm doing g of x plus h will be right here to the right of x. And so when I find g of x plus h, it's the area from a all the way to x plus h, the area under the curve. And so when I subtract the two, the red and the green, I really get just the area in between, which is this part in blue. Okay, so this would be equal to the blue area. Okay, and that's just me subtracting the areas. So as I recall, how I got the blue area is just subtract the areas. Alright, so now what happens if h is small enough? So for h being small enough, that would mean that x and x plus h are pretty close together, and we'll have, let's use purple, why not? So this distance from x to x plus h is h. Would you guys agree that if I took the height being f of x, at x, right here, this would be f of x, you'll get this rectangle in purple. That would be a good approximation, relatively, for the area on the curve. But if h is small enough, this purple rectangle becomes thinner and thinner, right? If h was smaller and smaller. So I can still find the area of the purple in relation to the area of the blue. So the area is approximately the area of the rectangle in purple. The blue area is approximately the area of the rectangle with the height of f of x and the width h. Okay. Oh, where did it go? And so, if this purple is a relative approximation for the light blue, I get that this implies that g of x plus h minus g of x, which is precisely the blue area, is approximately the area of the purple rectangle, which is given by the sorry, technical difficulties. Give me 1 second. Alright. So g of x plus h minus g of x, which is the blue area, is approximately the area of the purple rectangle, which is the width having h, times the height, which is f of x. Now, if h is small enough and also just a number, non-zero, correct, and we're assuming that h is greater than 0 at the moment, then I can divide both sides by h, so then I get g of x plus h minus g of x divided by h should be approximately f of x, since I divided both sides by h. And then, if I take the limit as my h getting to 0 on both sides of this, essentially, that is precisely g prime of x is equal to the limit as h goes to 0 of g of x minus g of x plus h minus g of x divided by h. That's the definition of derivative. And as h becomes very, very thin, as a rectangle becomes very, very thin because your h value is approaching 0, you're eventually getting no width, but you have that height, which is f of x that we were going towards, right? So this is true even if f is not necessarily a positive function like we began with f of x being greater than or equal to 0. So now that we have this concept a bit better, let us get into the fundamental theorem of calculus part 1. So, fundamental theorem of calculus 1, part 1. Well, what does this say? First of all, it says if you have a continuous function f on a closed interval from a to b, closed and bounded interval from a to b, then we get that the function g is defined by the fact that g of x is equal to the integral from a to x of f of t dt, like we were practicing earlier, for x being between a and b, or equal to them, which is going to be, so g is also continuous on a to b, and it is differentiable, just like we've kind of shown earlier, on the open interval from a to b, and the derivative g of x happens to be f of x. Okay, so now we want to prove this. So in order to prove this, let's start off with the fact that we're going to start off with what g is defined as the integral from a to x of f of t dt, and then we need to show that it is continuous, we need to show that it's differentiable, and we need to show that the derivative of g is precisely f. So let's start off with the fact that if x and x plus h is in your interval from a to b, so you can imagine, if you want a small sketch, here's a and b, and x is here, and then x plus h is within there. Okay, then we know that g of x plus h minus g of x, by the definition of what g is, it's the integral from a to x plus h of f of t dt minus the integral from a to x of f of t dt. We also learned that this first integral can be broken up into multiple parts. When you want to find the area under the curve sometimes, it might be easier to break it into smaller pieces, such as the integral from a to x of f of t dt plus the integral from x to x plus h of f of t dt. That's the first part, and then I'm going to try to write minus the integral from a to x of f of t dt right there. Kind of ran out of space since I wrote so big. Okay, so we get that. And then notice that this part and this part are exactly identical, so I can subtract them, leaving me with the integral from x to x plus h of f of t dt. So g of x plus h minus g of x is just the integral from x to x plus h of f of t. Now, if, as long as h not being 0, we can technically divide both sides of that equation that I just realized, g of x plus h minus g of x, which equals the integral from x to x plus h of f of t dt, right? I can divide both sides by h, and when I divide the right-hand side, I'm just going to write it as 1 over h instead. So this is equation number 2 that I'll reference later. And so now if h is non-zero, if h happens to be positive, so greater than 0, we also know already by our condition at the very beginning of fundamental theorem of calculus that f is continuous on a to b. So that means, so f is continuous not only from a to b, but from x to x plus 1 on this closed interval, because of the fact that this is within a to b, right? You can think about that diagram that I did earlier. Here's a, here's b, here's x plus h. The interval here is in between here. Okay, so it's f is continuous. So then we have, by the extreme value theorem, which states that if you have a continuous function and on a closed and bounded interval, then that means it attains its maximum and its minimum. So that means there exists a u and a v inside the interval from x to x plus h somewhere, such that f of u equals lowercase m and f of v equals capital M, where m and capital M are your absolute minimum and absolute maximum values of f on the interval that we're looking at from x to x plus h. So these are the largest and smallest values that we're working with. So if you're thinking about the diagram that I have right above as my number line, we have that u and v are somewhere in here, and I drew it in blue. Now, if you remember, we have a property of integrals. So by property number 8 of integrals, or even if you don't remember the properties, we can kind of just think about this. If you have a general function, right, and general function like this, and we're looking from a to b, then we shrunk it down to x plus h. Let me make this like more dramatic, maybe. Okay. I'm just purposely trying to make it a little bit more dramatic. If this was my function, we know that u and v are inside x and x plus h, where u is being the minimum that happens. And so the minimum looks like it happens about right there. So that would be where u is. And my maximum is like right there. So at v in my diagram happens to be exactly where like v plus h is. And so if this is my function f in black, then this value is f of u, which I'm defining as lowercase m. This v right here, f of v, is defined as my capital M. So these are the largest values possible and also the smallest value possible within this green region that I'm outlining for you. Okay? So if that's the case, taking my minimum here, if I wanted to approximate the area under this black curve, I can at least bound it below by this light blue rectangle. And so that light blue rectangle, which is property number 8 that it's talking about, the height of it is lowercase m, and what's the width of it, which is x plus h minus x, but the precise integral from x to x plus h of f of t dt is greater than that, because it's if I try to shade it in black here, you'll see that situation. It's more precise. And here's the red. The red is going to be this rectangle by using the height of the maximum. And so you can see that the area of the under the curve from x to x plus h is less than or equal to capital M, the height of the red rectangle, times the width, which is x plus h minus x. Okay, now it's a matter of simplification. So the property number 8 is just a way to estimate and bound your precise value of the area under the curve for your integral. So when I simplify, I get m times h is less than or equal to it's less than or equal to the integral from x to x plus h of f of t dt is less than or equal to capital M times h, and lowercase m is just f of u times h is less than or equal to this statement in the middle, which is less than or equal to capital M, was represented by f of v times this h. Now, if h is non-zero, and we are assuming right now that h is also greater than 0, we get that I can divide both sides by h, so I get this new equation number 3, where f of u times h divided by h is just f of u, which is less than or equal to 1 over h times the integral from x to x plus h of f of t dt, which is less than or equal to f of v, again, assuming that I divided everything by h just now. And this inequality, similarly, number 3 can be determined, this inequality here, can be shown for when h is less than 0. But that will be left as an exercise. So moving forward, now let h go to 0, because that's part of my definition of derivative is the limit as h goes to 0. Well, if I go back up to my diagram, if h goes to 0, x of x plus h, that point is moving to the left because it will be a little bit less closer and closer towards this x value. But if u is between x and x plus h and h is becoming 0, then u is also going to x as well. And v is also within this region. And so that means v is also going to x. So when h goes to 0, we can see that u is going to x and that v is also going to x. Okay? So now, if I think about the limit as h approaches 0 of f of u, well, that will be the same thing as the limit as u going to x of f of u. And why did I start off with the limit as h goes to 0 of f of u? I'm looking at the left-hand side of equation number 3's inequality. Okay, and then because we understand how h approaches 0 affects the u, it approaches x, I just rewrote it that way. And then when you work with limits, you know that you can do direct substitution if possible, so I get f of x. Now, the same thing applies if I looked at the right-hand side of my inequality in number 3. So I'm taking f of v, but then I'm going to take the limit as h goes to 0, and that will be the same thing as taking the limit as v approaching x of f of v. And so when I do that, doing direct substitution here, I get f of x. So then, if I look at equation number 3 and I apply the squeeze theorem, taking the limit as h approaches 0 on it, you can see that the left-hand part of the inequality and the right-hand part of the inequality is the same value. So you can see the squeeze theorem. It's squeezing the 1 over h times the integral from x to x plus h of f of t dt. So then we get that this is the middle limit as h approaches 0 of g of x plus h minus g of x over h. Remember that this part right here we showed earlier was just 1 over h integral from x to x plus h of f of t dt. Okay, I'm going to erase it now. And then we took the limit in front of it, so that's why we have that. And we, by definition, we know that this is just the notation for g prime of x. And on the right, by the squeeze theorem, here, we got that this was equal to f of x. So now, this is what we call equation number 4. So from 3 and squeeze theorem, we get this equation number 4. So what did we just showed here? We showed two things at this point. Looking at my conditions for what you need to prove, right here at this stage, we showed that g is differentiable, and we show that g prime of x is equal to f of x already. So if I go back to, we just showed this part and this part. Okay, scrolling back down, I need to show that g is also continuous. So jumping to the very end of it, for the moment, to show that it is continuous, recall the fact that recall, I think, Theorem 2.24, or in short, if, I'll put recall here, that if a function is differentiable, then it implies that it's continuous. So, based off number 4, g is differentiable, so this implies that g is continuous on your closed and bounded interval, and that was the third thing that we need to show. The third thing that we need to show for the fundamental theorem of calculus, part 1. Now, if you notice, when I started off with x and x plus h being in the open interval from a to b, so we try to make our lives easier to begin with, that they're not your endpoints essentially. Well, how do we work with the fact when it is the endpoints? Well, if x is a or if x equals b, you can modify the equation number 4 by just using one-side limits. So you can, equation 4 can be interpreted as a one-sided limit. Okay, and you'll be able to follow. So when I said that the theorem 2.24 differentiability implies continuity, I was also took into consideration this one-sided limit. And because we've showed all three parts with the given conditions, we are finally done with showing the fundamental theorem of calculus part 1. Hopefully that shows the beauty of the fundamental theorem of calculus part 1 for now, and let us do some quick, I guess, examples and calculations. I can't pronounce this very well, but Leibniz notation for the fundamental theorem of calculus part 1. Well, that means I can write it as, here's equation number 5 in case I need a reference later. Here's your integral from a to x of f of t dt, which is my g of x. And then if I'm taking the derivative with respect to x of all of that, that's g prime of x. And we know that g prime of x was just f of x. So this is just slightly different notation. So this is true when f is continuous In other words, I should have wrote this all in red, so let me change to red right now so that it stands out. So if we integrate first this portion, then we take the derivative, this portion, then we get the original function f, okay, which is the right hand side. So quick application. Example number 2. I want you to find the derivative of g of x equaling this integral from 0 to x of the square root of 1 plus t squared dt. Well, here's the solution. What is your function that you're working with? F of t is the square root of 1 plus t squared. We know it is a continuous function, right? Under the radical would never be undefined. So we know it's continuous. Now what does the fundamental theorem of calculus part 1 say? Well, this tells us that g prime of x is supposed to be equal to f of x. Well, if you already identified that f of t is the square root of 1 plus t squared because you have it from 0 to x here, then it's just a matter of putting x into that, and it becomes the square root of 1 plus x squared. That's the nice bit of beauty, right? G of x equals the integral from 0 to x to the square root of 1 plus t squared dt. Notice the setup here. F of t is just the square root of 1 plus t squared. It's what you're integrating with. And so if I take the derivative of the left-hand side, that's g prime, well, that'll be, if you look at the equation number 5, I'm putting d dt in front of this portion, essentially. And I get f of x, and f of x is just square root of 1 plus x squared. This is nice because if you're interested in physics, chemistry, or stats, they do use these things on more complicated situations. So if you're in physics, chemistry, or stats, they work with g of x equaling the integral from a to x of f of t dt. And so there's a function called, I think, Fresnel, if I pronounced it correctly, which is represented by capital S of x, but it's defined as the integral from 0 to x of sine of pi t squared divided by 2 dt. Now, based off your knowledge right now, it's a pain to find the derivative of this function. In fact, we don't even know how to find the integral of this that well still at the moment, because there's so many techniques out there. But if I wanted to find the derivative of this, derivative of capital S, that function would be equal to as simple as sine of pi x squared divided by 2, because my function that I'm working with is sine of pi t squared divided by 2. Okay. However, it does get a little bit more complicated than that. If I gave you an example that says find the derivative with respect to x of 1 over x to the 4th secant of t dt, notice here that your a is 1, but your b, your x, is no longer x, is x to the 4th. So we're actually going to need to use the chain rule with your fundamental theorem of calculus part 1. So as long as we let u be x to the 4th, then I could really write that the derivative with respect to x of the integral from 1 to x to the 4th of secant of t dt, that's equal to the derivative with respect to x from the integral of, well, 1 to, instead of writing x to the fourth, I'm going to write u of secant of t dt. But because we have to think of this as like the chain rule, and we're applying the derivative of this with respect to x, I'm going to take the derivative with respect to u of the integration from 1 to u of secant of t dt times the derivative of that upper limit here, du dx. So if you want to see this as, I guess, quote unquote fractions, you could kind of see that the du and the dx, du and the du cancel each other out, leaving you a ddx kind of thing, but not the best way to really see it. But we're using the chain rule here, right? Because this part is the derivative of the upper limit. And so now I get that from the first part right here, the derivative with respect to u, and it matches with this part, just u. That's just secant of u because that's my function, secant, times my du dx. Well, u is u equals x to the fourth, so take the derivative of that with respect to x. That becomes, using power rule, secant of u times 4x cubed. But what is u? Well, u is x to the fourth, so I should really put that back in. And that is what we get. Alright, now let's talk about the fundamental theorem of calculus part 2. First of all, it says, if you have a continuous function on a to b, then we get that the integral from a to b of f of x dx is equal to capital F of b minus capital F of a, where f is any, capital F is any antiderivative of lowercase f. That is to say that f, capital F, if I take the derivative of that, is equal to f, if you remember how we define antiderivative. So what's nice about this particular fundamental theorem of calculus, this is where you guys were saying that this stuff will make your lives so much easier. So when we were trying to find integrals, we first did it using the limits of your Riemann sums. But now it will be so much simpler, or so much easier, because of this fundamental theorem of calculus. So before we do this, let us prove it first. As a recall, that capital F is the antiderivative of f, so remember that if f was x, right? Lowercase f is x, then the antiderivative of that would be x squared divided by 2, but it may differ from a constant, so plus c. And also notice for the fundamental theorem of calculus part 2, we're working with a definite integral where your limits of integration is from a to b, where a and b are just specific numbers. Okay, here's a proof. First, let g of x be equal to the integral from a to x of f of t, just like we've kind of done before. Well, by the fundamental theorem of calculus part 1 that we've already shown, the derivative of this g will be equal to f of x, right? So we can see that well, what just happened? We can see that g, lowercase g, is just the antiderivative of f. Well, if capital F is any other antiderivative of f on this particular interval from a to b, well, that means it just takes the form. I'll probably use this as a reference later, so I'll just put a 6. That capital F is g of x, but changed by a constant, right? And this would be true for your x being between your a and b still. Well, not only that, we also know that g is continuous, and if g is continuous and you're adding a constant c to it, then capital F is also continuous. So we know that f and g are continuous on a to b. Well, if I take the limits by taking the limit on both sides of equation number 6, the one that I just wrote, where x approaches a from the right and x approaches b from the left, this is trying to think about the portion where x equals a and x equals b. So we can still have these still being true, even though my original number 6 is only between a and b strictly. So that last statement right here is good for me to say that f of x is equal to g of x plus capital C for all values of x between lowercase a to lowercase b, but it's closed and bounded with brackets. Now, that's true. Now let's look at the fact that if x equals a and for g of x, what would that look like? Well, this implies that g of a is equal to the integral from a to a of f of t dt. Well, that's 0. Equation number 6, looking at that with the fact that x equals a and b, that tells us that capital F of b minus capital F of a. So equation number 6, which is f of x equals g of x plus c, but I'm using it with a and b and I'm subtracting them. And the reason why I'm doing this, think about my fundamental theorem of calculus 2. This is the right hand side of my equal sign right now. So my goal is to now show that it's equal to the integral from a to b of f of x dx. So let's start off with this part. Capital F of b minus capital F of a. That's equal to g of b plus c, some constant, minus g of a plus another constant. And then if I subtract it by distributing the negative sign, I get g of b minus g of a. And what is g of a? Well, we just showed a little bit earlier, because we were thinking ahead, that it was 0. So that's just g of b minus 0. And, right, minus 0. And then I'll just erase that real quick. And what is g of b? Well, that is defined as the integral from a, and instead of writing x, I'm writing b, because b is x in this case, of f of t dt. So you can see that we've proven the fundamental theorem of calculus part 2. So the nice thing about this is that when I write the integral from a to b of f of t dt equals capital F of b minus capital F of a, notice that I just took the antiderivative of lowercase f and then I'm just plugging in the endpoints B and A and subtracting them. So, uh, so in the context of your antiderivatives, we can think of it as find your antiderivatives and then we subtract using the endpoints. That's like a quick way of thinking of what the fundamental theorem of calculus part 2 is. So then, trying to do this in some sort of context, we can start off with an application. If velocity, v of t equals your velocity, and s of t is your position function, and of course time is represented by t, then we can say that v of t is just the derivative of s prime of, okay? Right, we know that already. We've done this before. Take the derivative position function, we get the velocity. So if you want to think in a different sense, we can see that s is the antiderivative of v. And so when I write the integral from a to b of v of t dt, if I'm taking that integral or the area under the curve for your velocity function, that is just taking the antiderivative of v, which is s, plugging in your upper limit b and subtracting it from the antiderivative of v, which is s, and the lower limit a being plugged in. So this would be area under the velocity curve, which so area of the velocity curve is as simple as seeing it as it equals the the distance traveled from A to B. Alright, now that we have the beauty of the fundamental theorem of calculus part 2, let us do some examples of its application. So example number 5, if I ask you to evaluate the integral from -2 to 1 of x cubed dx, well, the solution to this situation is, first, can I apply the fundamental theorem of calculus on this? Well, the condition to that, let's go back to the top real quick, is that I need to make sure that my function f is continuous from a to b, and so look at where lowercase f of x is. It's inside your integral, and the limits of integration is a to b. So I need to make sure for my example here that my f of x, my lowercase f of x, is defined, and we know it's x cubed. And not only that, we know it is continuous from -2 to 1. So with that being said, I can use the fundamental theorem of calculus part 2. Well, what does that say? I need to know what my antiderivative is, which is capital F of x. So that antiderivative of lowercase f would be x to the 4th divided by 4. Or if you want, you can write 1/4 x to the 4th. But then, using the fundamental theorem of calculus part 2, we get that the integral from -2 to 1 of x cubed dx should be equal to the antiderivative of the upper limit minus the antiderivative of the lower limit. And so I get 1 to the 4th divided by 4 minus -2 to the 4th divided by 4. And when you do that, I get, well, I could factor out a 1/4 for simplicity first. So I get 1 minus -2 to the 4th is -2 times -2 is 4 times a -2 is -8 times a -2 is -16. No, +16, sorry. And so I really have 1 minus 16, so then that becomes -15 times the 1/4, so -15 over 4. So look at how nice my result is for finding the integral of this situation instead of trying to graph it and doing the limits of my Riemann sum. Okay? And also note that when I took, I'll put a star here, note that the fundamental theorem of calculus part 2 says that we can take or use, any, keyword any, antiderivative of lowercase f. So what we chose here, the most simple scenario of the antiderivative was when f of x, capital F of x, is equal to 1/4 times x to the fourth. What could have happened is that I could have used 1/4 x to the fourth plus like 7 or something, and it would still work. Or 1/4 x to the fourth plus capital C, because the general antiderivative, remember, you get an extra constant at the very end. Okay, so the final answer to this question is when you take the antiderivative in this particular spot right here, we use the most simple one. We don't have to worry about the plus c, because when you subtract them, that same constant would then be in the first portion here, and it'll also be over here, so that when you subtract it disappears on us, so it becomes 0. So that's why we can just take the most simple version and not worry about the plus c. Okay. Now in terms of notation, be aware that when I write f of x, capital F of x, and I put a bar, I put a little a and a lowercase b as such. Well, the a is my lower limit and my b is my upper limit. So when I translate this notation, this means f of b, f of my upper limit minus f of my lower limit plugged in. So when I write the fundamental theorem calculus part 2, the integral from a to b of f of x dx, that's equal to f of x, capital F of x, evaluated from a to b as such, where, of course, f, capital F, is the antiderivative of lowercase f, so that means f, capital F prime, is just equal to lowercase f. As an extra note, other people might use notation where instead of a straight bar down, they use a bracket, like one-sided bracket, or they might even do like double-sided bracket. But all of this depends on context, right? You have to understand when people use what. For my situation, I'll always use that one straight bar, the one that I wrote at the very top. Okay? Let's do some more examples. Find the area under the curve. That's a parabola. So y equals x squared for when x is between 0 and 1, essentially. Well, the solution to that is the area is just equal to the integral from 0 to 1 of x squared dx. Agreed that if you're trying to find the area of your under the parabola, that's the same thing as taking the integral, concept-wise. And where do you want to take the parabola? The area under the parabola from 0 to 1. So that's your limits of integration. So now look at this situation. If I want to use the fundamental theorem of calculus part 2, you want to look at your f of x, identify it, which is x squared. It is definitely continuous because it's a polynomial, it's continuous everywhere. So definitely be continuous from 0 to 1. So that's checked. And then if I know the antiderivative, what's the antiderivative of x squared? That's 1/3 x cubed, and I'll take the simple case for the moment. So now going back to this, a equals the integral from 0 to 1 of x squared dx. I'm going to evaluate this, so that'll be x cubed over 3, because that's the antiderivative of x squared. Then I'm going to apply the limit from 0 to 1. I'm going to evaluate it from 0 to 1, or at these places, essentially. So now when I take my upper limit, plug that in, that'll be 1 cubed over 3 minus 0 cubed over 3. That's my capital F right here, and that's my capital F here, evaluated at 1 and evaluated at 0 respectively. And so the answer to this is just 1/3. Once we get the fundamental theorem on calculus part 2, all of this integration becomes so much nicer and easier. Example number 7. Let's find the area under the curve again. Find area under the curve. Well, what happens if we have something as complicated as cosine? And we're doing it from x equals 0 to x equals b, where b is between and including 0 and pi over 2. Well, the solution to this, identify your function. Well, f of x will be cosine of x. That's your cosine function. We know it's continuous everywhere. And if I want to find the antiderivative of this, capital F of x, that would be sine of x. Because the derivative of sine is cosine, so we know we're good there. So the area under the curve represented by capital A is the same thing as taking the integral from 0 to b of your function cosine of x dx. Because we're integrating from 0 to b, that's our key point. And so when I take what's the antiderivative of cosine? That is sine of x. And where are you going to evaluate it? At 0 and b. And then we're going to take the upper limit, plug that in. So sine of b minus sine of my lower limit, 0, plugged in. And what is sine of 0? Sine of 0 is 0, so then I'm just left with sine of b. Now, if you're trying to visualize this, here's 0, here's pi over 2. My y equals cosine of x function. Here's my x-axis, here's my y-axis. Cosine of 0 is 1, so right here is at 1. And at pi over 2 is 0. So my goal was to find the area under this curve. Right? But this was when b was pi over 2. So this example that I'm showing you right here is when b is pi over 2. So if we focus in, if we take b to equal pi over 2, the area on the curve, area under this curve, under the cosine curve, from 0 to pi over 2, well, if b was pi over 2, we know I could just replace b with pi over 2 instead, so then it will be sine of pi over 2, which is equal to 1. Okay? So in our first example, in black, we found it generically for any b value from 0 to pi over 2. The result would have been sine of b. But if you know what b value that you're working with, like pi over 2, then you just plug in b at the very end now, since we got a general formula there. Alright, example number 8. Well, my question is, what's wrong with what I'm about to do as shown? So the integral from -1 to 3 of 1 over x squared dx is equal to, we'll take that and rewrite this as x to the negative second power dx. That way when I take the antiderivative, I can write x to the negative first power divided by -1. And then I'm going to evaluate it from -1 to 3. And so when I plugged in 3, I get 3 to the negative first over -1, which minus -1 to the negative first divided by -1. And so I get 3 to the negative first power is 1/3, divided by -1 is -1/3. Negative divided by negative is a positive, and then I'm left with plus 1. Oh, not plus 1. Plus -1 to the negative first power, if you need to see that step. And so that is just -1. So I end up with -4/3. So what's wrong with this? Well, if you think about it, what did I, first of all, should have recognized? If I'm visually thinking about this, from a visual point of view, is that why is my answer negative? When you know that 1 over x squared if I think about the function, is always going to be greater than or equal to 0. So we know by one of our properties of integrals, then the integral of 1 over x squared from a to b dx should also be greater than or equal to 0, because you know that your function is greater than or equal to 0 always. So that's already a part that makes us question why this is wrong. Well, not only that, when we talk about the fundamental theorem of calculus, it applies to continuous functions. That's why in the first few examples, I pointed that out. So you can't apply this to 1 over x squared because it's not continuous specifically on -1, 2, 3 that you were trying to integrate using. There's an infinite discontinuity at x equals 0, because then the denominator is 0. So the integral from -1 to 3 of 1 over x squared dx does not exist. And we'll see that a little bit more in detail later. But that's why we can't apply the fundamental theorem of calculus on this particular example. So let's summarize the very last part here. You could think of derivatives, so differentiation and integration, essentially as inverses of each other. And I'm talking about inverse process of each other. So what's the fundamental theorem of calculus? We first have the fact that suppose that f is continuous on a closed and bounded interval from a to b. And one of the first part of it was, if you know that g of x is defined as the integral from a to x of f of t dt, then we know that the derivative of g is just the original function f of x. And the second part of it was, if I take the integral from a to b of f of x dx, then I just take the antiderivative of the upper limit, capital F of b, minus the antiderivative evaluated at the lower limit, capital F at a. Okay? And then of course I'm just going to write what it says. F is technically any antiderivative of f. That is to say, when I say antiderivative, that means that the derivative of capital F is just the original function, lowercase f. So again, I'm trying to summarize things. So remember that also in part 1, we were able to write the derivative with respect to x of the integral from a to x of f of t dt is equal to f of x. The left-hand side is just g prime of x. And this is telling us that I can integrate a continuous function, then so that's this part. Then if I take the derivative with respect to x, so I differentiate it now, I end up on the right-hand side, I get the original function f. Now, also, our very last bit, if I integrate from a to x when I use f prime of t dt, that's equal to, well, what's the antiderivative of capital F prime? Well, undo that derivative, that would just be regular capital F, and evaluate it at the upper limit x minus the lower limit a. So what does this one say? Well, if you recognize that the original function that you work with is the derivative, so if I derivative of capital F, that's the inside part right here, then I integrate it, that's the entire left-hand side now, I get back the original function f, but notice I have minus f of a here, so except for a constant f of a, because the variable is the x. So minus f of a is just a constant. And there you go. Nice and summarized.